Going to work with power series. Now, power series is kind of a really cool subject. Basically, you're dealing with infinitely long polynomials. Now, you've dealt with polynomials before. Is it hard to differentiate a polynomial? Is it hard to integrate a polynomial? Yeah, very hard, Carson. Very, very hard. So polynomials are very friendly functions to work with. It's just you got to take careful when your polynomials get, I don't know, infinitely long. There's a lot that goes into it. So we're going to work with some. This is a power series. That's your infinitely long polynomial and has a center at A. So that's where everything, all the interesting stuff is happening. Now you can kind of relate to center because you've dealt with polynomials before. So here's a cubic polynomial, and I can shift the center, and that's just going to move, where some of the interesting things happen. You can do the same kind of thing with parabolas, but again, you're just shifting the center, is just shifting where, the interesting thing, in this case, the vertex is happening. Now, that interesting point, like I said, that's your center. The problem that we're going to run into working with these infinitely long polynomials is, do they converge? And it doesn't do us much good if these series don't converge. And there's going to be a couple possibilities for their convergence. It could happen that they only converge when x equals a. Now do a little Gedanken experiment for yourself, which Einstein used to do those, right? Thought experiments. If you put in x equal a, what's going to happen to all these terms in the series? Let me zoom in a little bit. If you put in x equal a, somebody said it, James? Yeah, you're going to get zeros, right? They're all going to be zeros. And this infinite sum of zeros is going to be zero. So that's certainly a series that would converge. But does it converge in more interesting cases, more general cases? Now, the types of convergence that you get can vary between a couple extremes. This is basically, it only converges at that one point. It could converge for all x, or it could converge in some areas in between, so for some x's. And if that's the case, then you have what's called a radius of convergence. That's going to be r. So that radius of convergence says, well, as long as you're within r of this value of a, it's going to converge. So let's relate to it in terms of circles first. So when you have a circle, what's the distance across here? Yeah, that's your diameter. All right, so got a diameter. But if I didn't go all the way across, if I just went, a little bit of a ways, starting at the center, then what's that? That's your radius. And in a similar way, if you had convergence at a point, or a series that was centered at, say, A, you could get, that it converges to, say, a plus r and a minus r. So it's within some range that you get this convergence. And if that's what happens for you, then this is going to be your radius of convergence, and your radius of convergence is going to be r. Radius of convergence is r. Now, sometimes we'll write an interval of convergence, and that interval of convergence is just, well, this point to this point. So the interval of convergence is related to, but a little different than your radius of convergence. Your interval of convergence is going to be these points, here to here. So in this case, it'd be a minus r to a plus r. And what we're eventually going to have to do is we're also going to have to check for convergence at the endpoints. Sometimes you'll get it, sometimes you won't. But that's where we're headed. We got to test these series for convergence. Now, in section 11.9, we're going to start building up these series to actual functions that we're interested in. Right now, it's just going to seem like kind of random stuff, but it is leading to something a little bit more substantial. Let's start out with example B here. So, example B. And as I mentioned, as we got started, I'm just going to do a few of these and then let you work on some as well. So we've got this series, the sum from I equals 1 to infinity of -1 to the n, x to the n, over the square root, it's not the square root of n, what is it? 7th root of n? All right, thank you. 7th root of n. What's one big thing that's different about our work here versus the work we did up till this section here? There's one big difference in this summation.
Is that new?
Yeah, the x is new. All right. Up till now, we just had a series based on, n, but now we've got kind of two variables working here, n and x. Now, x is going to make this a function of some value, so p of x. We want to know where it converges and when it converges. For the most part, you're going to be applying the ratio test ad nauseum from here to the rest of this course. So we want to decide when this converges. When you apply the ratio test, we're going to be taking the limit of, as n approaches infinity, of a sub n plus 1 over a sub n. To converge, what's the requirement for the ratio test? What do I need to have so that this actually converges? This limit has to be less than 1. All right, so that's what we're going to apply to all the terms in this series. So our a sub n is just kind of right here. That's our a sub n. What would a sub n plus 1 look like? Well, let's take a look. That's going to be -1 to the n plus 1, x to the n plus 1, over the 7th root of n plus 1. And now we need to form the ratio of those two terms. It is an alternating series, that's wonderful, but the alternating part's really not going to make a difference because we're going to be dealing with the absolute value of this. So, okay, let's take a look here. Let's form the ratio a sub n plus 1 divided by a sub n. I'm going to form that ratio and simplify it. So it's going to be this divided by this term. Can we save ourselves a little bit of work here at the start? When you divide by a fraction, what happens? Multiply by the reciprocal. I don't think I need to write this divided by this and then do all that. Let's just multiply by the reciprocal right away. So it's going to be -1 to the n plus 1, x to the n plus 1, over the 7th root of n plus 1, times the reciprocal of this term, which is going to have your 7th root here, -1 to the n, x to the n. Let's simplify that before we bother taking its absolute value and its square root, or absolute value and its limit. Now, generally speaking, when I do this for myself, I don't even bother writing the -1s here because we're eventually going to be taking the absolute value and they're just going to disappear. But if you're comfortable doing it this way, that's fine. Can you see any simplification? X to the n, all but one of them cancels, right? So I'm left with an x there. And then, let me rewrite it. All but one of these signs cancel out, so I'm just left with a -1 here. Overall, I'm left with -1 times x times the 7th root of n over the 7th root of n plus 1. That's my simplified ratio. As you're doing these problems for me on an exam, please take the time to write limit and keep on writing limit until we're all done with the problem. The limit as n goes to infinity of this ratio is going to be the limit as n goes to infinity of the absolute value of negative 1 x times the 7th root of, well, let me write it like this, 7th root of n over n plus 1. Let me make that 7 a little bit closer to the root, 7th root there. Now the negative 1 is going to disappear. This limit is as n approaches infinity. Does it really depend on the x at all? No. So I can take the absolute value of x out in front. That's just a constant as far as this limit is concerned. Take a look at the limit as n approaches infinity of the 7th root of n over n plus 1. Do I need the absolute values? Well, if we're going as n approaches infinity, this ratio has to be positive, right? You're just going to be dealing with positive numbers, and the 7th root of something positive is still going to be something positive, so we really don't need the absolute value there. Can anyone suggest what this limit's going to be?
1.
Yeah, 1. Because you're going to take the limit as n approaches infinity. Inside here, that ratio is going to 1. And when we take the 7th root of 1, you're still going to get 1. Maybe I should write it like this. Maybe you'll be a little more comfortable. But the limit inside here is going to be 1. So it's going to be 7th root of 1, or just the absolute value of x is the limit. So that gives us conditions under which this is going to converge. Because what was our condition from the ratio test? What has to be true about this in order for this to converge? That has to be less than 1 in absolute value. So continue, absolute value of x is less than 1 in absolute value of x is less than 1. Now when and where is that true? Well, with the absolute value inequality cases, you can kind of do this. That means negative 1 is less than x is less than 1. So you got this nice interval. You can kind of repeat this inequality with a negative on the other side. That's where this is true. By the way, that also tells us our radius of convergence. This series only converges for anything between negative 1 and 1. Our radius of convergence is this number right here. Let's see. Ethan? No. All right, I was going to ask. Man, everyone's ducking out of the way. Ah, off the rim. All right, let's try a different one here. So this is the radius, thank you, of convergence. Right there. That's that big 1. But sometimes you're going to be asked to find the interval of convergence. Before I work on that part of it, how are we looking on what we've done so far here? Are we okay with this? Is there something that maybe I went over a little too quickly that I can go over before we discuss the interval of convergence?
Can you show the end of the problem again?
Sure.
Okay. That checks out. Okay, so.
Okay. You're welcome. Now, the problem is we need to also investigate what happens at the endpoints. Do we get conversion at the endpoints? We don't know. So you're going to have to one at a time test them by plugging them into the series. So check for convergence at the endpoints. Okay, cool. Let's do that. So our series was the sum from I equals 1 to infinity of -1 to the n, x to the n over 7th root of n. Let's test the series at x equal 1. Now if I'm checking the series for convergence at x equal 1, I'm actually going to put in the 1 into this series. So it's going to be the sum from I equals 1 to infinity of -1 to the n, 7th root of n, and then I'll have 1 to the n power. So let's put in that 1 there. What's going to happen with this one then? Well, what's 1 to the n? It's just 1, right? Don't need to take out our calculators for that. I equals 1 to infinity of -1 to the n over the 7th root of n. Ah, I remember all those 10 tests that we had for convergence. This is where we use them. This is why we practice the 2-minute drill. What's looking good here? What test do you think you would use to decide convergence or divergence of this one?
Alternating series.
Alternating series? Yeah, absolutely. So this term here, -1 to the n, is going to make the series alternate. So use the alternating series test. You could also rewrite this as sum from I equals 1 to infinity. You know, I don't actually think it's really helpful, but you could write it as -1 to the n over n to the 1/7. But the series alternates. Eventually, this series is going to get really, really close to 0. And because it's an alternating series, it passes the AST. So we're going to get convergence by the alternating series test. So it converges at the endpoint. So we're going to keep that endpoint as one of the places where this converges. Let's test the other one. Let's test at x equal -1. At x equal -1. So that's going to be the sum from I equals 1 to infinity, -1 to the n, -1 to the n again, over the 7th root of n. We got to simplify some things in the numerator. Any suggestions? Can you think of something, Kaiser?
-1 to the 2n.
Good. -1 to the 2n. Let's play around with that carefully. Keep in mind, you're just adding exponents. When you multiply things with the same base, you're adding exponents over 7, or 7th root of n. And now this -1 to the 2n, that's going to require a little bit of thought here. So let me kind of do that down at the bottom here. -1 to the 2n. I think Kaiser sees what's going on. I'm not sure it's terribly clear to everybody else, but maybe it is. I don't know. In any case, let me rewrite this. Let me rewrite it as -1 to the n and then to the 2. Is that this? You know, actually, I need to do that the other way around. Is this the same thing? Does this have the same value? Well, if I remove those parentheses, this exponent would multiply this one. So I'd have 2 and n. But that helps me out on the inside. What's -1 squared? 1. What's 1 to the n? 1. So our little nice trick here is to notice that that's effectively 1 in the numerator. I'll pause for a second. That was a little hocus pocus, but are we good with that? All right. So this is the sum from I equals 1 to infinity of 1 over, let me write it as n to the 1/7. We still have to determine if this series converges or diverges. I know one of you has the answer.
Is it supposed to be an I or an N?
You know what? I've been writing I but using n. Let me be consistent on that. Thank you. So
We don't put it in for the n value. We put it in for
yeah, no, I should be writing n for all of these. Thank you. So n, 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 n. Thank you. And one more, n. Okay. So again, knowing all those different series from your 2-minute drill. Does this series converge or diverge? Diverge. Why? P series. P is less than 1. So great. So it diverges at -1. It converges at +1. Our interval of convergence, so our interval of convergence is going to be -1 to 1 with bracket at +1. There you go. Nice. Only 15 minutes worth of work for one problem. But I promise not to put more than a dozen or 2 dozen on an exam.
Our Christmas present.
Yeah, early Christmas present. Remind me to do the mathematics of Santa Claus at some point. Yeah, that one's pretty fun. All right. Any questions on this one? Any little follow-up? 4 pages worth of notes so far. Got one problem done. Okay. Let's try. Gina, you say you're looking forward to this?
No, I said the worst part is when you make a mistake and you realize it at the end and you raise the calculator to work.
I was so happy that when Kaiser raised his hand to point out a mistake, my heart was sinking. I'm like, please don't tell me I got to erase everything. It was just the index. I was like, whew. I was really, really happy it wasn't anything devastating. Maybe. All right, let's try a different one. So this would be example C. So example C. We got the sum from n equals 2 to infinity of x to the n plus 1 over 5n factorial. And I want to point out a couple things here before we really get going on this problem. One of them is that this series starts at 2, which is a little bit unusual. It's different. That's okay. Does it make a difference as to where this starts, as to whether or not this is going to converge? No. You can throw out a finite number of terms, and it's not going to affect the overall convergence or divergence. You're just adding or subtracting a little bit here from terms at the beginning. This one starts at 2. That's fine. The previous one starts at 1. Some of these series start at 0. How come I can't start this series at 0? This would be undefined at that point. It diverged immediately after the first term if you had a 0 in there. So the fact that it started at 1 actually makes sense here. They started this one at 2. Let's take a look at something else here and try and, get an intuition about where this is going to converge or diverge. Now let's see, the slowest growing functions that we had were the natural log, right? ln of n. And that was less than our square root functions. And that was less than our polynomial functions. And that was less than our exponential functions. And that was less than our factorials. And that was less than n to the n. So let's take a look at where we're at on this spectrum with respect to these terms. Which runs grow fastest? Now this is a function of x and n, but overall it's some kind of a polynomial growth term. So you're here on the chart. That's smaller, in fact it's much smaller than a factorial. So the factorial is going to grow really, really fast. And you got a factorial here. I'm thinking this is going to converge, and it might converge for everything because this is going to grow a lot slower than this will at some point. Let's see though. Let's actually form our ratio test. Let's figure out what a sub n plus 1 is going to look like. So a sub n plus 1. This is our a sub n, this term right here. A sub n plus 1 is going to be x to the n plus 1 over 5 times n plus 1 factorial. You might want to take the time to simplify this a little bit. That's going to be x to the n plus 2 over 5 times n plus 1 factorial. Okay. Let's start by simplifying this ratio, the absolute value of n plus a to the n plus 1 over a sub n plus, or a sub n. As before, I'm just going to multiply these two ratios instead of divide them. So it's going to be x to the n plus 2, 5 n plus 1 factorial times 5n factorial over x to the n plus 1. Okay. Let's take a look here. How is this ratio going to simplify? Anyone see anything?
Do we cancel out the n factorial?
If I cancel out the n factorial, what's left?
N plus 1.
Yeah, well done. So in the denominator here, this is really 5 times n plus 1 times n factorial. So when I cancel this out and this out, I'm still left with a 5n plus 1. What other things can I cancel out? Does anyone see anything interesting? Cameron?
I was more confused why doesn't the 5 get canceled out too?
Well, it can. That's one of the other things you can cancel out. You can cancel out the 5. Sure. What else? X to the n plus 1. How many x's are going to be left? Just the one. So it's going to be x over n plus 1. And now let's take a look at the limit. So I want the limit as n approaches infinity of my a sub n plus 1 over a sub n is really going to be the limit as n approaches infinity of this x over n plus 1. Keep in mind n is fixed here, right? Doesn't really matter, or excuse me, x is fixed here. It doesn't really matter what x is. You can take that out. It's going to be x times the limit as n approaches infinity of 1 over n plus 1. Nice. What's that limit? Harlan? 0. Yeah, so you get x times 0. And x times 0 is 0. So this converges no matter what the value of x is, right? So therefore converges for all values of x. So its radius of convergence is infinity. Nice. Nice. Now, if you wanted the interval of convergence would just be negative infinity to infinity. Obviously, we're not testing any endpoints here. So that's your R right there. And there's your interval of convergence. So nice. A little bit easier than the last one. Okay. That was a little nicer. Are we okay with example C here? Anything, Syed? Thumbs up there? Nika? Ben?
Why didn't you test for the interval?
What's that?
Why didn't you test for the interval of convergence?
Well, if the radius of convergence is infinity, then it's going to converge to the right infinitely far and to the left infinitely far. And the endpoints there aren't things that I can actually drop into the function. I can't drop in infinity and negative infinity. So, yeah, we're just going to say if the radius of convergence is r, and it's r because it doesn't really matter what the value of x is. This series is going to converge for all values of x. So you've got an infinite radius of convergence. There's no endpoints here to test.
Thank you.
Appreciate that. Thanks for the question. Okay. Let's see. Fine. Let's move on to example G. Example G. Sum from n equals 1 to infinity of square root of n over 7 to the n times x plus 5 raised to the n. So this one's a little different. This one has a shifted center. The first two did not. What's the center of this shifted polynomial? Negative 5. All right, so it's the value of x that would make this equal to 0. So negative 5 is our center. Okay. Let's try and find out where and when this converges. We're again going to apply the ratio test. So let's take a look at our term a sub n plus 1. And if you're watching this at some point in the future, pause the video and see if you can't write down that a sub n plus 1 term for yourself. I'll give you guys a chance to write it down as well. See what that term looks like. Okay, looking pretty good from what I saw. Square root of n plus 1, 7 to the n plus 1, x plus 5 to the n plus 1. So let's put that together and see if we can't find this ratio. Now, I don't necessarily need the absolute values because everything's going to be positive here. Well, I guess I'm not really sure about the x plus 5 to the n plus 1 term, so I will keep that. There's going to be absolute value of square root of n plus 1, 7 to the n plus 1, times, I'll put this up in the numerator, x plus 5 to the n plus 1 over 1 times the reciprocal of this function here, which is going to be 7 to the n, square root of n, and 1 over x plus 5 to the n. So I still need that absolute value there. Yeah, I guess I should have been a little bit more careful with the absolute value in our last problem. Carried that absolute value all along. Had I done that, had I had the absolute value here, then I would have had the absolute value here, and here, and here. We still reach the same conclusion, but note to self to be a little more careful with that absolute value. Lots of simplification here. Let's go on a simplification free-for-all. What are some of the things that you see can simplify? Alicia? Amro? See anything they can simplify?
The n plus 1.
N plus 1 where?
And the first two. Yeah.
This one? Bottom?
Yeah, like the 7 plus 1.
All right, 7 to the power n plus 1. That's going to cancel all but one of these. Good job, thank you. What else? What else can cancel out?
X plus 5 to the n.
Yeah, x plus 5 to the n. We're going to get rid of all but one of those. So this disappears, and I'm going to be left with x plus 5 to the n. Let's clean that up a little bit. So it's going to be the absolute value of x plus 5. Let's see, what else do we have? Over the square root of n and square root of n plus 1. Okay. Let's see, yeah. Let's see, we got another 7 here too, right? That's in the denominator. Let's take a look at the limit then as n approaches infinity of this term. So the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. That's going to be the limit as n approaches infinity of the absolute value of x plus 5 times square root of n plus 1 over 7 square roots of n. Now, a lot of this stuff doesn't really depend on the limit, so I can take it outside of the limit. I'm going to keep it in the absolute value, except you don't need to keep the 7 in the absolute value. So that's going to be equal to the absolute value of x plus 5 over 7 times the limit as n approaches infinity of, let's just write it as the square root of n plus 1 over n. Let's see this do. Yeah. So it's going to be the absolute value of x plus 5 over 7 times what? Yeah, this whole limit is just going to be 1. What has to happen in order for this to converge, though? Yeah, this has to be less than 1. Absolute value of x plus 5 over 7 has to be less than 1. Yes, sir?
I'm just a little confused on how it equals 1, because isn't it infinity plus 1 over infinity?
So let's take a look at that. a little bit more closely. So what's really going on here is that I'm going to interchange the limit and the square root because this is a continuous function. So I can create this, or I can rewrite this as the square root of the limit as n approaches infinity of n plus 1 over n.
And then use L'Hopital's rule.
You could use L'Hopital's rule here. What would L'Hopital's rule tell me?
It's 1 over 1.
Which is,
1.
so you get the square root of 1, which is 1. Good with that? Okay. Let's solve this. If this is true, that's going to be the same as x plus 5 is less than 7 in absolute value. Here's where we can use a little shortcut that I don't like to show some of my beginning algebra students, but I'll be happy to use here. That's going to be the same as negative 7 is less than x plus 5 is less than 7. So it's going to converge when x plus 5 is in that range. Last but not least, we've got to subtract 5 from all sides here. If we do that, we end up with negative 12 is less than x is less than 2. But wait, we're not done. Does anyone remember what else we have to do here? Yeah, we have to check the endpoints. By the way, this is an interesting number here for us. Does anyone know what that really reflects? I should have had the Jeopardy think music queued up here. My bad. So this number here, that's R, your radius of convergence. So we get a interval of convergence that's 14 units wide, and that's our radius of convergence is 7. But what's our interval of convergence? Do we get convergence at either of these 2 points? That's going to take another 5 or so minutes to test. So let's play around with that. Gina, something about that doesn't look right?
No.
You good? Okay. Let's keep going. So we'll test the endpoints. Test. Let's see. We'll start out with negative 12. X equal negative 12. In the series that we started out with, the sum from n equals 1 to infinity of the square root of n over 7 to the n, x plus 5 to the n. Okay, so at negative 12, when I plug in a negative 12 there, let's see what I get. I get the sum from n equals 1 to infinity, square root of n, 7 to the n, and negative 12 plus 5. What's negative 12 plus 5 going to do for me? Well, let's simplify what's in here first. Sum from n equals 1 to infinity of the square root of n over 7 to the n, negative 7 to the nth power. Which is n equals 1 to infinity. Now, I'll kind of slow it down here a little bit. That's going to be square root of n. I'm going to write this all together. Negative 7 over 7 raised to the n. They're both to the nth power, so I'm just going to put them in one big fraction, like that. how does this simplify? It's just -1 to the n. So you got an alternating series. But I don't think you want to use the alternating series test here. Well, you don't need to. What are you going to do to decide the convergence or divergence of this series? Sophia? No? Nth term test, right? What's going wrong with this? How come we can just look at this and go, yeah, that's not going to converge? Clyde just said it to you. Nth term test. Are these terms getting smaller? As n goes to infinity, does the square root of n get smaller? No, you're getting bigger and bigger terms, and it is alternating, but these terms don't go to 0. So by the nth term test or by the alternating series test, remember the alternating series test still says this term has to go to 0, and it's not. So by the AST or the nth term test, the series diverges. So did we get convergence at that point? No. We got to go back and test the other point. So the other point was at x = 2. So let's do that. And let me do this. So we'll test x = 2. Let's see if we fare any better on that one. So it's going to be the sum from n = 1 to infinity, square root of n over 7 to the n, and 2 plus 5 to the n. Let's try and make this one a little bit faster. 2 plus 5 is 7. So this term and this term are essentially the same. You get 7 to the n and 7 to the n. They cancel each other out. Square root of n. Jonathan, what are you thinking on this one? Converge or diverge, or what test would you use? Diverge, right? Same kind of problem that we had here with the other series. These terms aren't going to 0. Square root of n is going to get bigger and bigger and bigger. And if you add a series of bigger and bigger terms, you're going to eventually head to infinity. So diverges by the nth term test. Now notice at the end here, when I'm just trying to decide if we have convergence at the endpoints of our interval, I'm not really going through all the work here. This is why we spend a lot of time working with the 2-minute drill, is because after you do a lot of work, you still have to do more work. And I want this work to be kind of quick. I want you to be able to look at these things and go, yeah, that's going to diverge. Yeah, that's going to converge. So that you get those endpoints really quickly. And overall, for this series, this is going to converge between -12 and 2. That's the interval of convergence. So we didn't pick up convergence at the endpoint at all. Nice, nice. Now we're kind of at a little decision point. I could do one more, but these problems take like 10 or 15 minutes, and I wanted to give you a chance to work on at least a couple of them here, so you can kind of sort out some of the things that are working on. I could do one more, but let me take a question from Hannah first.
For the diverges at 2, is it still the parentheses or the brackets?
Well, because it diverges at 2 and -12, we're using parentheses rather than brackets.
Oh, okay.
So if we got convergence, like we did with our previous one, then we put a bracket at that point where it converged. If you don't get convergence, then it's going to get a parenthesis.
Oh.
Yeah, appreciate the question. Anything else? guys want to brave some? Try a couple on your own. Let's try and do 2 on your own. All right. So let me stop the video here and let you get working on things.